Hello, here we are, part one of the concepts over projectile motion. No mathematics in this part. Here we go. Path of a projectile, pretty simple, makes a parabola, this nice parabolic arc. We can of course increase the size of that arc by throwing it up higher, or change the width of the arc by throwing something harder in the horizontal direction, but it's always a parabola. We have this term range, which describes how far horizontally our object ends up. And of course, the maximum height could also be called the altitude. Turns out when we talk about a projectile type of motion, you have to break it into its two parts. It's horizontal and it's vertical motion. Turns out you treat them no different than as if you were talking about an object moving horizontally, at least that motion of that projectile, or an object moving vertically. In other words, if an object is going up like this, the object at this point is moving in this direction and in that direction at the same time. If you can think about things in advance, tell me about a horizontal motion. Gravity doesn't affect things horizontally, which means it moves on its own inertia. Gravity does affect things vertically, so gravity is going to be the defining detail as to how high that's going to go and how much time it's going to spend in the air. In other words, they're independent of each other. What it does horizontally does not affect how high it's going to go, or what this does vertically has no effect on how far it's going to go, except when it comes to the time it is in the air. Let's look at a snap photography picture of a bush baby that's jumping through the air. You can see the nice parabola it makes. And look at the spacing. Horizontally, this bush baby is covering the same distance in the same amount of time. Horizontally, this thing is moving because of its own inertia. It's not speeding up. It's a constant velocity. So horizontal motion is always at a constant velocity. That same picture can be looked at vertically. On the left side, he's going up. On the right side, he's going down. Notice the spacing. Looks like an accelerated object. So vertically, the bush baby is accelerating. So notice what's going on. Upward spacing is getting smaller. Downward spacing is getting bigger. If we were to sketch this, we start here, and then it's big, it's getting smaller and smaller and smaller and smaller and smaller. And on the way down, it looks identical. There's no difference. You couldn't tell one side from the other. Because here we're accelerating. And here we have, actually this is a negative acceleration, this is a positive acceleration, right? Up is positive, down is negative. So let's put this together. If we look at the guy on the right, and we were to scale this so that every second we were to place the ball where it's at, and we know the scale is 1 centimeter. Per the instructions down here, 1 centimeter is 5 meters. We could certainly draw the positions. If you do the math very quickly, do a time versus distance. In seconds is the time, 1 second, 2 seconds, 3 seconds, 4 seconds, and the distance is meters. Using the formula, d equals 1/2 gt squared. Time for 1 second is 5 meters. For 2 seconds, it's 20. 3, it's 45. And 4, it's 80. Go ahead and pause the video and check it out yourself. This should be a very familiar formula. So if we use 1 centimeter as every 5, well, after 1 second, it's gone 5 meters. 2 seconds, it's gone 20, right? 5, 10, 15, 20. 3 seconds, it's gone 45, which means we're here. In 4 seconds, it's 80 over here. So that's an object if we just drop it. We know that when you throw an object, like this guy is, we talk about its horizontal motion, we know it's going to continue straight line, constant speed. It moves at its own inertia. But what happens when we combine this horizontal motion with the vertical motion? Because we know on Earth, when you throw something, it's going to start accelerating vertically as it moves horizontally. So after 1 second, it's actually right here. It started in his hand, actually fell 5 meters. 2 seconds, it moved over, but it fell a total of 20 meters. 3 seconds, it moved over, the same distance horizontally, but it fell a much greater distance, 45. And so forth down the line, and we get a nice half parabola. Looks a lot like an object you might throw. Again, the horizontal motion of this object is completely independent of its vertical, and when you put them together, you get that parabola. Think about how things behave horizontally. They don't accelerate. They move on their own inertia. Think how things behave vertically. Throw an object up. It goes up, and then as it slows down, then it comes down. And it accelerates as it's moving vertically. Every projectile has those two motions, horizontal and vertical motions. If we look at a photo of a ball being dropped, the red one, in the case of the right-hand picture, this one, and one being thrown, the yellow one, being thrown horizontally. Notice again, the spacing horizontally is the same. It's moving by its own inertia, but the spacing vertically is not the same. It's getting bigger each second, each moment in time. Put them together, and that's what you have. Think about what's going on with this next series of questions. Which ball hits the ground first? Well, take a look. Neither. They're both falling vertically. Doesn't matter what it does horizontally. Remember, they are independent of each other, the horizontal and vertical motion. If they're both moving vertically, then they're both falling at the same rate. Which ball has the greatest vertical distance? Well, they started at the same height, and therefore they end at the same place. They both fall the same distance. So that sets the stage for the rest of this. Describe the horizontal motion of B, because it's the only one that has any horizontal motion, and the vertical motion of both of these. Well, again, horizontal motion, as you suggested, as you heard, look at this, it's a constant velocity. And of course, the vertical motion is not constant, it is accelerated. What role does gravity play in the time? Think about it. If right now things are falling at 10 meters per second every second, that's the rate at which their velocity changes. That's our acceleration due to gravity. What happens if gravity is greater? In other words, it makes it go 20 meters per second every second. I think it's safe to assume that it should take less time, right? Greater gravity means less time, shorter time. Well, what does gravity play in the horizontal distance? Well, remember, it's all about the time. That's the only connecting factor. If you're in the air for a less amount of time, well, then you can't go as far. If I travel for only 1 minute, I'm going to go a certain distance. What if I traveled for 2 minutes? I could certainly go twice as far. So in other words, more gravity means shorter distance. What if we launch something upward? So we have one firing this way as we just drop one. This one has to go up and then down, and then it's finally at the same position that our first one started. I would think that the one that you dropped would hit the ground first. How could we increase the range of this ball? Remember, time is the big issue, right? If you're in the air longer, you're moving a longer time, you can go farther. We know a little bit about gravity, right? Less gravity means you're in the air longer. Distance in the y direction. So as we increase the height, so maybe we originally had a distance of this, maybe let's increase it to this. So you're in the air longer because you have farther to fall. Again, there's that time issue. And of course, the velocity in the x direction. Instead of traveling this distance each moment in time, what if you traveled this distance each moment in time? Traveling faster horizontally, you're going to go farther horizontally in the same amount of time. Which brings us to the age-old question. If I fire a gun horizontally and at the same time I drop a bullet, which hits the ground first? Even though this gun is firing horizontally, gravity is still going to make it fall. You just don't notice it because it's traveling so fast horizontally. You don't actually get to see it fall. So, because they're both traveling vertically due to gravity, they both hit the ground at the same time. It doesn't matter what this does horizontally.